Here we have another example, similar prompt to the last example that we did. So we have a function f of x equals negative 2x cubed plus 3x squared plus 120x. We want to find the intervals where f of x is increasing, the intervals where f of x is decreasing, and then any local extrema that we may or may not have. So if I want to determine where a function is increasing, where it's decreasing, finding local extrema, all of those things require finding the critical points first. So I'm going to find my derivative, which here isn't too bad. We're just going to use a power rule. So I should have negative 6x squared plus 6x plus 120. And here's my derivative. I want to find the critical points, which means I want to find places where f prime of x is equal to 0 and find places where f prime of x does not exist. So first, let's take our function, set it equal to 0. Negative 6x squared plus 6x plus 120 is equal to 0. I see a common factor of negative 6. I'm going to factor that out, negative 6, and that will leave me with x squared minus x minus 20 here is equal to 0. And then I can take this expression right here and factor it further. I need two numbers that multiply to be a negative 20, add to be a negative 1. So that would be x minus 5 times x plus 4 is equal to 0. Taking each factor, setting it equal to 0, gives me x equals 5 and x equals negative 4. I know that these are both critical numbers because we're working with a polynomial. That polynomial has domain of all real numbers. So that means that 5 and negative 4 are definitely critical numbers. We also then need to consider the case where f prime of x does not exist. Here, our derivative, though, if we look at it, negative 6x squared plus 6x plus 120, that's a polynomial, which means that our derivative exists everywhere. So f prime exists everywhere. And what that means for us is that there are no additional critical points for this case. Again, when we're working with polynomials, we won't see any critical numbers pop up because f prime of x does not exist. But again, it's a good habit to still consider it, to think about it for when we consider functions that are not polynomials, when we're thinking about root functions or rational functions, things like that. So these are the only two critical points I have, 5 and negative 4. Next, I want to construct my number line. So I'm going to construct a number line for f prime. I've got two critical numbers. I've got negative 4 and positive 5. And just as we've done in most of the problems here today, I'm going to take a number in each one of these intervals and plug them into my derivative. Actually, before I do that, I also want to make a note to myself, well, how did I come up with negative 4 and positive 5? What's the behavior of the derivative? Well, the derivative is equal to 0 there, so I'm going to make a note to myself that the derivative is 0 at each of those points, and that's what tells me I'm going to have a horizontal tangent line. So now I'll take a number in each one of my intervals and plug that into my derivative. So let's start with negative 5. We'll work with f prime of negative 5. This is equal to, here, I'm going to use this factored form just so that the arithmetic is a little bit easier. Negative 6 times, let's see, I'll have negative 5 squared minus, negative 5 minus negative 5 minus 20. And again, I'm just checking to see whether we end up with a positive or a negative. So here I've got 25 plus 5 minus 20. Here negative 6 times, this will be 30 minus 20, 10. I end up with negative 60, which means that my derivative is negative on the left-hand side of negative 4, which means that my function is decreasing on that side. So there we go, there's the first part. Now I need a number between -4 and +5. 0 would work pretty well here. And just to be consistent, I'm going to once again use this factored form. If you would like to fall back and work with that original function, you can absolutely, or excuse me, the original derivative, not the original function. If I want to work with the original derivative with this guy right here, you'll get the same result. It's just, I always just say pick whatever you think is going to be easier. But just to be consistent, I'm going to plug it into this factored form here. So f prime, let's do this right here, f prime of 0, this is -6 times 0 squared. Oops, hold on, what did I forget? I forgot my parentheses right there. There we go. -6 times 0 squared minus -0 minus 20. So I have -6 times, let's see, this will be 0 plus 0 minus 20. I have -6 times -20. I should have a positive 120. So my derivative is positive in between -4 and +5, which means that my function must be increasing on that interval. Need one last number to the right of +5, so how about +6, I think would be a good choice. F prime of +6. Let's plug that into our derivative. Again, I'm going to use this factored form right here. So -6 times 6 squared minus -6 minus 20. Here, let's see, -6, I'll have 36 plus 6 minus 20. So let's see, 42, -6, 42 minus 20, I'll have a positive 22, which, oh, let's see, that should be -132, I believe, -132. My arithmetic may be off there, but remember it's the sign that I really want right there. It's the sign of that number. My derivative is negative, which tells me that my function is decreasing on that interval. So if I want to start to talk about my answer here, I can start to give some of my answer. Let's do that in this upper right-hand corner. I can say, well, my function is decreasing on -infinity to -4, -infinity to -4, and +5 to +infinity, 5 to +infinity. It is increasing on that interval in between from -4 to +5. So I have my intervals where my function is increasing or decreasing. Now I want to look at my number line right here, and I want to see, okay, do I have any local extreme values? So I'm going to look for sign changes in my derivative. So let's look at -4. Do I have a sign change? Well, on the left-hand side, I've got a negative derivative. On the right-hand side, I've got a positive derivative. So I'm changing from decreasing to increasing. If you need to draw yourself a picture, it's decreasing and then increasing. Well, yeah, that is a local minimum. So that means that x equals -4. This is the location of a local minimum. So I know that x equals -4. We've got, and I'll make a note down here, we have a local min at x equals -4, but I also want to give the y value with my answer. So I'm going to take that -4, I'm going to plug that into my original function f of x in order to find the y value. So let's see, let's see if I can remember this function. Let's write it down. F of x was -2x cubed plus 3x squared, I believe, plus 120x. Let me just double check. Plus 120, yes. So plus 120x. So I'm going to take -4 and plug this into my function. So f of -4 equals -2 times -4 to the third power plus 3 times negative 4 squared plus 120 times negative 4. And let me grab my graphing calculator here just so that this arithmetic goes a little bit faster. I should have negative 64 times negative 2. I'll have 128 plus here 48 minus, let's see, 480. All right, let me just double check. Times 4, yep. So 128 plus 48 minus 480. I have a y value of negative 304. Oh my goodness. So I have a local minimum. I'm going to include this with my answer. I have a local minimum. And I can say this a few different ways. If you want to give it in function notation, f of negative 4 is equal to negative 304. Or you could give it as an ordered pair, negative 4 comma negative 304. I also want to look at, well, what's the behavior at x equals 5? What's going on there? So at x equals 5, well, on the right-hand side, or excuse me, on the left-hand side of x equals 5, my derivative is positive, so my function is increasing. And on the right-hand side, my function is decreasing. I have a negative derivative, so I'm changing from increasing to decreasing right here. So I'm changing from increasing to decreasing. This point to me looks like a local maximum. So this is going to be a local extreme value. And once again, just like I did before, I'm going to take that x value and plug that into my original function right here, because that's what's going to tell me the y value. So f of 5, this is equal to negative 2 times 5 to the third plus 3 times 5 squared plus 120 times 5 here. So I should have, let's see, negative 250 plus, here I'll have 75 plus 600. So let's see, negative 250 plus 75 plus 600 gives 425. So I have a local maximum. At f of 5 equals 425, or if you'd like to give the ordered pair, 5 comma 425. So here's everything that the problem asked me for. I know where my function is decreasing. I know where my function is increasing. I know where I have a local minimum. I know where I have a local maximum. If I wanted to make a rough sketch of this, I won't go too far into detail because this function, we've got some very large y values here. But just to make a quick, really rough sketch of our function, let me see, actually, do I have room up here? We'll do this right here. Block this off. So if I wanted to construct a graph here, let's say negative 1, 2, 3, 4, 5, and then positive 1, 2, 3, 4, 5. And let's label our y-axis by hundreds, negative 100, 200, 300, 400, 100, 200, 300, 400. I'm going to take the local minimum and the local maximum values first, and I'm going to plot those. So negative 4 comma negative 304, let's put that somewhere right around right here. And 5 comma 425, I'm going to have a point, let's say right around there. And again, I want to check the behavior of my derivative at those points. We said the value of the derivative at both of those points was 0, which means I have that horizontal tangent line. So at negative 4, we've got a minimum. So we've got a minimum right here with a horizontal tangent line. If you need to, we might adjust it just a little bit. and then a maximum over here at positive 5. Again, I should have that nice round top horizontal tangent line. And we may need to do a little bit of adjusting here. It looks like we've got a ways to go, so let me fix this up. So my function is decreasing, and then increasing, and then decreasing once again. This is a pretty good rough sketch of what my graph looks like. It tells me where do I have my local minimum, where is my local maximum. It sort of catches the behavior at each one of those points. So that's what I'm going to be looking for. Again, we are going to be practicing graphing functions a lot, both in this section, in the next section, and actually even in section 4.4 as well. So these are skills that we will continue to practice as we move forward.